Okay, so for our first problem here, we want to draw a sketch of a trough approaching a fixed end. A fixed end means that the string or spring or whatever the wave is traveling in is like tied to something, like a wall. Okay, something that essentially the wave wouldn't travel into. Okay, so we have a trough, okay, and it is traveling towards that fixed end. Okay, since the fixed end is something it can't travel into, it's going to do what when it hits it? What happens to most waves when they hit something they can't go into? They bounce off. They reflect. Okay. Now, is this reflection going to be upright or inverted? Is it going to be a trough coming back or a crest coming back? Remember, we said yesterday that at a boundary with something that's more dense or more difficult to travel into, the reflection would be opposite, inverted. So you're going to have to refer back to your notes because obviously a lot of you are looking at me like you have no idea what I'm talking about. This is what we did yesterday. So you're going to have to go over that. I told you there's going to be diagrammatic questions on your unit exam about this stuff. Okay, so what we should see here is the second part of this diagram is that. Okay, that pulse reflects back inverted and goes back the other way. So let's look at question number 2 here, where we're drawing waves before, during, and after complete destructive interference. So you've got a diagram just like this in your notes. Okay, we went over it when we talked about interference. So before complete destructive interference, I have to have two pulses that are moving towards each other that are opposite. If they're not opposite, they're not going to destructively interfere with each other. Okay, so this would be before. This would be during, and then after we would have this. Okay, the important part of the after picture is recognizing that the waves are not permanently destroyed. Okay, they are only destroyed during the actual overlap. Okay, and after that they travel on unimpeded. Okay, how many people have done number 3? Okay, so for that sketch there, or is the wave moving from a faster medium to a slower one, or from a slower one to a faster one? Okay, in the second picture, I have what kind of a reflected wave? Okay, so this wave going in is upright. Okay, this wave that is a reflection off the boundary is inverted. All right, the wave that goes into the new medium is not only shorter, but also smaller in amplitude. So is it moving, is this a medium that is faster or slower than the first? Slower. Okay, if we got an inverted wave, it's automatically slower. Okay, the shape and size of this wave also tells us, or just confirms, that this is in fact a slower medium because the wavelength has decreased. All right, so if I gave you a question like that on a test, that would be your justification. Okay, you would say there's an inverted reflected wave which only happens off a more dense medium, and the transmitted wave is shorter and has a lower amplitude. Therefore, this must be a more dense or slower medium. Okay, so you'd have to have that justification in there. All right, so you can try these ones here now. Okay, so looking at number 4 here. So we have a spring, which is quite heavy, okay, and we have a very light string tied to it, which is then tied to a wall. Okay, so at point A, that's the boundary between the spring and the string, right? Which one is it most likely easier for a wave to travel through? A very light string or a heavy spring? Light string. Okay, it's going to be way easier to travel through the light string than it is for it to travel in a big metal spring. All right. So as this pulse approaches point A, when it reaches point A, when a wave reaches any boundary, okay, two things can happen. Some of the wave will be reflected, and some of it will be transmitted. That's really all you need to know for part A. Okay, what happens when the pulse reaches point A? Some of it will get reflected, some of it will get transmitted. That's what happens at any boundary. Okay, is the pulse reflected from A erect or inverted? Okay, Erect means upright. Yeah. Okay, upright or inverted. So when it reflects, if this medium is less dense, the reflection will be upright. Okay, what happens when the transmitted pulse reaches B? All right, well, B is a fixed end. Okay, it's tied to there. The wave's not going into the wall. All right, so it's just going to reflect off, and the reflection will be inverted. Always off a fixed end, the reflection is inverted. Okay, number 5, we have a spring that's running across the floor, so it's really, really long, and it goes out a door where we can't see the end of it. We make a wave in that spring, and then a few seconds later, an inverted pulse comes back. All right, so did I attach the spring to a door or a wall, or did I just leave it hanging loose on the floor? Yeah, I had to attach it to a wall. If I'd let it hang loose on the floor, not attached to anything, I would have got an upright pulse coming back because the wave would have left the spring and gone into air, which is less dense. Okay, but in this case, because it came back inverted, it had to be attached to something more dense than itself. Everybody all right with that? Okay. Okay, this one has to just do with universal wave equation. If I want to make waves on a rope that I'm making, if I want to make them longer, should I shake the rope faster or slower? Which one will make longer waves? Slower. Yeah, if I go slower, my waves have a longer period, okay? And as a result, they also have a longer wavelength. If I shake it really, really fast, the waves will all be really, really short, okay? Everyone kind of follow on that? All right. Give you a few more minutes here. Work on these last ones. Okay, so 7 is very much like one we already did, and then 9 and 10 have to do with linear superposition with interference. Okay, and I always ask a question like this one here, okay, on the unit exam, where I ask you, here's 2 waves, they're overlapping, draw what the medium will look like as a result. Okay, I always have a question like that. Okay, so for question number 7, we've got a thin rope and then a heavy rope. Okay, so is the heavy rope going to be faster or slower for the waves traveling through it? It's going to be slower, it's more dense. All right, so when the pulse gets to point A, as always, some will be transmitted, some will be reflected. Right? In this case, more than was reflected in the previous example with the spring and the string. Okay, so when it gets to A, we'll get some reflection, and that reflection will be upright or inverted? It's going into a heavier, more dense rope. The reflection will be inverted. Okay. And when it gets to B, B is a fixed end. It can't travel into B, so it's going to reflect, and it's going to reflect which way? Upright or inverted? Inverted. Okay. For number 8, okay, what's one property of waves that never changes? Frequency. Good. Okay. Now, in this diagram, okay, we want to draw the resulting waveform. That means these waves are on the same medium, like it's a spring or a string or something like that, okay, but they're in the same place at the same time, so they're going to interfere. Now, are these waves in phase or out of phase with each other? They are in phase. When one is up, the other is up. Okay, they have similar wavelengths. All that's different is their amplitude. So, according to the principle of linear superposition, what I'm supposed to do is add the amplitudes together. So the resulting waveform, okay, should be 6 tall. Okay, so my resulting waveform would be the green line. Right? Like I say, there's always a question like that in the written response part of the unit exam. Okay, I give you 2 waves and ask you to draw the resulting waveform. Okay, what kind of interference is that? Constructive. Austin, question? Yeah, I would give you some sort of reference so that you would know how big to make it, yes. Okay, so what kind of interference is occurring at point G? All right, so at point G, first wave is up, second wave is up. This is constructive interference. All right, at I, one is down, the other is up. This is destructive. Okay, at K, same thing. One's down, the other's up. That's destructive. And at O, one's down, the other is up. Destructive interference. Okay, was that one on there? I remember seeing that one. Yes, they can still interfere. Right? I wouldn't ask you to draw the resulting shape because it would just be a garbled mess. Yeah. Okay, how many people are done 11? All right, work on 11 because there's always a question like that on the unit exam as well. So we'll take a little bit of time here. Okay, work on 11. We'll go through it and then we're going to talk about standing waves. All right, so let's have a look at this one here. So we've got the two-speaker question again. Okay, and the person who is observing is 6.8 meters in front of one of the speakers. Right? We know that the speakers are 6.42 meters apart, okay, and that they are producing sound that moves at 340 meters per second and has a frequency of 400 hertz. Right? What determines whether this person hears a loud or quiet sound? What kind of interference needs to happen for them to hear a loud sound? Constructive interference. Okay, so basically what determines whether there's constructive or destructive interference at this point is how many wavelengths does the sound travel from each source to the listener. Okay, if the difference in travel is a full wavelength, then they're in phase and the person hears a loud sound. If the distance is a half a wavelength, then they're going to arrive completely out of phase and we're going to hear a quiet sound. So first thing we need to find is the wavelength. Okay, so wavelength will be V over F, so that'll be 340 over 400 hertz. Okay, so we've got 0.85 meters as our wavelength. All right. What we don't have is the distance from the second speaker to the person, so we got to do a little Pythagorean theorem to get that. So we'll have the square root of 6.42 squared plus 6.8 squared. Okay, so that's going to be 9.351. Okay, we'll keep all those decimals when we do our calculations, but 9.35 meters, okay, is this side of the triangle. All right, so now I need to find out how many wavelengths are there in 6.8 meters, how many wavelengths are there in 9.35 meters. Once I figure that out, then I'll know whether the person hears a loud or quiet sound. Okay, so to do that, I've got to divide the two sides. So I'm going to take that number first and divide it by the wavelength, which was 0.85. All right, so that's 11 wavelengths. Okay, so there are 11 wavelengths on this side. And then I got to do the same thing over here, 6.8 divided by 0.85. Right, and that's exactly 8 wavelengths. Okay, since there's no halves, this is obviously what kind of interference? Constructive interference, because the difference in travel is 3 full wavelengths. Okay, so yes, one has to travel quite a bit further than the other. If they're far enough apart, that might sound weird, okay? But if they're just producing a general tone, you wouldn't really notice, okay? But the difference in travel is full number of wavelengths, so we hear constructive interference and a loud sound. All right, questions on that one? Okay. All right, so I need you to go to lesson 17 here in your notes package, standing waves, okay? Standing waves, it's basically what is responsible for the operation of many, if not most, musical instruments. All right, we want to get repeating waveforms to set up inside of an instrument so that we produce a certain tone, okay, for a certain length of time. In order for that to happen, we have to produce the waves continuously, but the waves also need to reflect. And they need to travel back and interfere with the waves we're currently producing. Okay? In doing so, they will interfere with each other at predictable points that will cause constructive interference and destructive interference. Obviously, we want to harness the constructive interference because that is going to result in a louder sound. So most musical instruments that resonate are designed to channel sound in such a way that it will amplify itself naturally. All right, so the shape of a guitar isn't by accident. Right? Wind instruments aren't shaped the way they are by accident, and you cover up certain holes and you essentially lengthen or shorten the wavelength of sound that can be produced by allowing the air to escape through different places. Right? So we'll kind of look at all of that stuff here. All right, so a standing wave, when it's not in a sound wave, so a wave that you can see, okay, occurs when two waves travel through the same place at the same time, two or more waves. Okay, the pattern itself is the result of a bunch of interference patterns. Okay, so what I'll do here is I'll get my assistant Peter to come back up and hold on to one end of this spring, okay, and I'll show you a few kind of simple standing wave patterns here. All right, so those are standing waves. Sound waves do the same thing, it's just that we can't see them because they're traveling in air, and air is transparent, so we don't really see the disturbance of a longitudinal wave when we get a longitudinal standing wave. All right, so that's what we were doing there just a minute ago, okay? This was our simple first pattern here on the top, okay, where we had constructive interference through the middle, and we had destructive interference at either end. When I shook the spring twice as fast, then I got twice as many places where there was constructive interference. Okay, this wave here, the top wave, is twice as long as the first one. If I drew a full cycle of that, it would go like way over here. Right? That would be one full cycle of that wave. Whereas in this picture, a full cycle of the wave is actually within the frame. Right? It's half as long as this one was. Everybody follow there? Okay. And that resulted from me shaking the spring twice as fast. Okay, in this pattern, I get, how many wavelengths are on here? 1.5. Okay, there's one full cycle right here. Okay, that's one full cycle, and then this is another half a cycle. So we have 1.5 wavelengths on the spring in that situation there. Right, but I had to shake the spring three times as fast as the first time, okay, in order to get that. Standing waves occur at what we call resonant frequencies. Right? So this is what we call the fundamental frequency, or F1. It's the first frequency that sets up a standing wave pattern on the medium. Okay? This is F2. It's twice as large as F1. Okay? And then this is F3. It's 3 times as large as F1. But there's only certain frequencies that do that. If I don't shake the spring at those frequencies, I just get a jumbled mess. Okay? And you could kind of see that when I was trying to get them started. It didn't really look like anything until I found the right frequency, and then it was easy to keep that going. All right? But there's only certain frequencies that will set up standing wave patterns for a certain medium. Right? Now, if I was making this pattern and then I backed up a step, the pattern would disappear. Okay? Why would the pattern disappear if I back up a step? In backing up a step, what do I do to the medium? I change it. I would put more tension in the spring. And as soon as I do that, it changes the speed at which the waves travel, which changes their wavelength, which means the frequency I'm using is no longer one that is going to produce a standing wave pattern. I have to find a new one, okay, in order to get that standing wave pattern to show up. All right, so any change in the medium will result in a change in the standing wave pattern. This is how you tune a guitar. All right, you turn the, I don't know what the little knobs are called. Tuning knobs is what I call them. Okay, the ones that crank up the tension or release the tension in the guitar strings. Okay, when you turn those, you change the tension in the spring, or sorry, the string, and that changes the speed at which the waves can travel on it. Right, as a result, it changes the wavelength. Okay, that is on that spring, and as a result, it sounds different. Okay, I keep saying string. Okay, and it will sound different. Right, you probably noticed if you've ever plucked one and then turned one of those, it sounds really weird as you turn the knob. Okay, so all of that kind of goes together. Okay, terminology. Nodes. Okay, the term node refers to any places where there is destructive interference. Okay, so that's all the ends. Okay, and any places in the middle where the spring does not appear to move very much. Okay, those are places where there is complete destructive interference. All right, the opposite of that are antinodes, where there is complete constructive interference. Okay, terminology for the waveforms. Okay, the waveforms, obviously the first one that we had, okay, we called the fundamental frequency. Okay, and then we use, so we have fundamental frequency as our first one. Okay, we don't use these overtones. Okay, the fundamental frequency is often called the first harmonic. Okay, because it's the first harmonic frequency that sets up a standing wave pattern, right? This one is our second harmonic. Third harmonic, and so on. Okay, the reason we don't use the overtones is the numbers are off. Okay, when we use second harmonic, it matches up with the number of antinodes. Third harmonic matches up with the number of antinodes. It just makes more sense to do it that way. Okay. Now, it's important to know those terms because I could give you a question that said you have this spring that's this long and you are shaking it at a frequency that is the second harmonic. So you would need to know, okay, in a second harmonic, there's 2 antinodes, 1 full wavelength on the spring, and that allows you to do some calculations. Okay, so you need to know the terminology for that reason. All right. Okay, so each standing wave pattern that's produced, okay, and you can see that we were able to produce 3 on the spring we were using, okay, happens at a unique frequency. That frequency is determined by the speed of the waves on the medium, so the medium itself, okay, and the wavelength of the waves. All right, so those unique frequencies go in a series, the smallest being F1, and then F2, and then F3, and so on. What do you mean, 1.5? So this situation here? Like this is 1.5 wavelengths here. That's F3. Yeah. Half of one of these? You can't. Remember, it's got this is an attachment point over here, right? So this is a point where there's always reflection. There always has to be a node at either end for a standing wave on a spring. Okay, when we talk about air columns, which is how wind instruments and stuff work, then you'll have antinodes at either end. Okay, in open air columns, you'll have antinodes because there's actually nothing there. The reflection occurs off the inside of the tube. Okay, so again, remember, we're not going to use these overtone terms. Okay, we're just going to use the harmonic ones. Okay, and they always coincide with the number of antinodes that are on there. Right. So for our first harmonic frequency, there is 1/2 of a wavelength visible. Okay, for our second harmonic, there is 1 full wavelength. For our third harmonic, there's 1.5 wavelengths, and so on. Each harmonic frequency will have another 1/2 a wavelength added on. Okay. Did you guys sign in with Nancy? All right. Questions on that terminology and those diagrams? Everyone okay with those? All right, so standing waves arise because an identical wave travels along the string, it reflects, it comes back, it meets a whole bunch of other identical waves that are still traveling back and forth. New ones are being produced, so they're always being added in, and that's what gets that increased amplitude. Again, I only had to move the spring about, let's say 3 or 4 inches at the most, and I was getting movement of the spring that was several feet. Right? There's a lot of waves on there that are interfering with each other. They continue to travel and they continue to add to that amplitude. All right? Now that's, again, when we watched the Tacoma Narrows Bridge the other day, that's the reason why the Tacoma Narrows Bridge collapsed, is waves could travel along it, they would reflect off the other end of the bridge and they'd come back and they'd meet waves that were being produced, okay, by the wind. And so more and more waves started to travel along the bridge and interfere with each other constructively. You could see, okay, that there were places where on that twisting, we had a big antinode right in the middle, right? We had 2 nodes at either end where it was fixed, okay? It just so happened that all the waves that were being produced on there happened to all have the same wavelength, okay, the same frequency, and because they were on the same bridge, the same speed, which meant that it just kept interfering with each other in the same spots. Now, with that bridge, okay, each side of the bridge has a different tension. Therefore, the waves can't travel at the same speed on both sides. They can never get a standing wave pattern set up now, right? Because they simply can't do that. Okay? Because they can't travel at the same speed, they're never going to have the same wavelength. They're never going to have the same frequency. Okay? They're just not going to be able to interfere and make a standing wave pattern on that bridge anymore. Right. That sort of makes sense? All right. So this is what I was talking about a minute ago here with the standing waves. Okay, we have the reason we have a node at each end is because that is where reflection is occurring, and because it's fixed, that wave is always going to produce its exact opposite at this point. So this crest is turning into a trough when it hits here, which means there's always total destructive interference at the two ends. All right, questions on that? Okay, why we have the nodes at each end? All right, so musical instruments, okay, and standing waves. Right, with a guitar, okay, if you want to produce a low frequency sound, then you pinch the string on, what is it called, the fret? Okay, I'd call it like the handle, but I don't play any musical instruments. Fret, okay, now I have. Okay. So you pinch the string on the fret, that's this part up here. You make it, you pinch right near the end, so you produce a really long wave. A really long wave has a low frequency, right? So as a result, you hear a very low-pitched note. If you want to hear a high-pitched note off of the guitar, then you pinch the string against the fret much closer to the, this is the bridge, right? Okay. I think someone told me one time it was the bridge. Okay, so you pinch it a lot closer to that and you get a shorter wave. The shorter wave will have a higher frequency, right? What's fixed here is that this is all the same string, and as a result, all these waves travel at the same speed. So all you can do is change the wavelength, and that will produce a different frequency. It doesn't change the frequency, it produces a different frequency. Okay. Everybody all right with that? So this wavelength here is 0.6 meters, but when I pinch half of that, okay, I get twice the frequency. I get twice as high of a note, okay, as I would have before. Making sense on that? All right, so now that's showing obviously an electric guitar, but with an acoustic guitar, okay, it's got the hole in it, okay. So the sound waves, the vibration of the guitar string, okay, is over that hole. That's what the point of maximum vibration should be, okay, ideally. Those sound waves go in to the resonant cavity. That's the hollow part of the guitar, okay. The shape of that guitar channels those waves, allows them to reflect off the interior, and essentially makes the whole guitar resonate. And as a result, then, you get a much larger sound than you would if you covered up that hole and just picked one of the strings. Okay, it wouldn't be nearly as loud because you're not allowing the sound to go into the resonant cavity and amplify itself. All right, if you've ever like plucked an electric guitar that's not plugged in, okay, it doesn't make very much noise. Right, but an acoustic guitar with the same thing, okay, produces quite a bit more. Okay. Yeah, I think that's all I need to say about the string instruments. All right, for wind instruments, okay, obviously we're not using a string, right? Wind instruments either use the vibration of the person's lips or a reed, okay, which is, it's actually a reed, isn't it? Like it's a piece of reed. Anyway, you blow across it and the reed vibrates back and forth, and it then puts sound waves into the air. That gets channeled through, okay, the shape of the wind instrument. Right, so if it's like a saxophone or something like that, okay, then it goes through the tube, and what you do is you change the length of the tube by pressing the keys. Okay, if you press a key, you allow air to escape in a different place, and that will either lengthen or shorten the length of the tube that's vibrating, okay, or that's resonating. Right. So what we do then, okay, is by changing the length of the tube, we change the wavelength of the sound. Right? And again, it's just like then it's just like the guitar. Longer waves produce lower frequency sounds, shorter waves produce higher frequency sounds. So all we do is change the length of the resonance tube. That's probably most evident with a trombone, okay, with the slide. Right? So when they slide it out and then they slide it back in, they're very clearly changing the length of the resonance tube in order to produce different notes. Okay. All right. So there's two different kinds of air columns. There's open air columns and closed air columns. Most wind instruments are an open air column. That is, they are open at essentially both ends. Right? The only musical instruments that would be a closed air column would be those that would be used at a hoedown. Okay, so like, you guys ever watch the show Moonshiners on Discovery? If you don't, you should. It's like redneck engineering. It's really good. Okay, they do all kinds of creative things. All right, but when they would finish a batch of shine, they would blow across the top of the shine bottles. Okay, and you guys have all done that, blown across the top of a bottle and hums. Okay, but it produces a different frequency depending on how much liquid is in there. Okay, because it's not the liquid that's vibrating, it's the air column. So the longer the air column and the less liquid that's in there, okay, you get longer waves and a lower frequency. When it's nearly full, it creates a very high frequency of sound. Okay, so as the party went on, the frequency of the sound would get lower and lower, okay, as they blew across the top of the bottle. All right, so we're going to look at closed air columns first. So in a closed air column, if I blow across the top of it, okay, I'm going to produce standing wave patterns of different kinds. Okay, but what happens is the waves travel down the tube and they hit the end that's closed, and they reflect off of that in the same way that the waves traveling along the spring bounced off the hands of the two people holding it. Okay, so they reflect off the bottom and they interfere, and we get a standing wave pattern that looks like this. Okay, so this first one here. How many wavelengths is that? Even less than half. It's a quarter. Okay, remember that this shape is one full wavelength. All right, so if I only have this much, that's only 1/4, right? If I get to here to the first node, that would be 1/2, 3/4, and then 4/4 after that. All right, so the first standing wave pattern that we get in a closed air column has 1/4 of a wave in the tube. Okay, so this would be a very, very long wave, and this would have a low frequency of sound. Right? If I could use something different, then I might get I would get 3/4 of a wave in here. Okay, or in this case, 1 1/4. Okay, or 1 3/4. Right? It goes up each time. All right. What if in the tube, instead of getting like all of these have an antinode at the end of the tube, which means they all make sound. Okay, what would this one do? If I had that waveform in the tube, what would it sound like? It would be what? Stuck in the tube. Okay, but what would it sound like? What's at the top? Instead of an antinode, it's now a node. What kind of interference happens at a node? Destructive. Okay, so if the air at the end of the tube isn't moving, what do I hear? Nothing. All right. The problem with closed air columns is they resonate at a lower range of frequencies than an open air column, which is why most musical instruments are an open air column. They resonate at a much wider range of frequencies. All right. So what I'm going to do here is I'm going to show you this. I'll get our resonance tube out because I think we have time for that. All right. So what we got is this first resonant point at 0.2475. Okay. That was this waveform in the tube. Okay, because it was the first resonant point we got. So that was when there was 1/4 of a wavelength in the tube. Okay, the second point, which was 0.73 meters, okay, is when we had this waveform in the tube. Okay, the one that was representing 3/4 of a wavelength in the tube. So with those two numbers, can I figure out what the wavelength of the sound is? Okay, so that's what we're going to use those 2 points for. Okay, I know that 0.2475 equals 1/4 of lambda. Everyone all right with that? Okay, so if I divide the 1/4 over to this side, I should get lambda. So 0.2475. Whoop. All right, so we got 0.99, so almost exactly a meter. Okay, and we said that this point, the 0.73, represented 3/4 of a wavelength. So if I want to find lambda, I would divide both sides by 3/4. Should I get about the same number here? Should be pretty close. Right, so we'll have our 0.73 divided by 0.75. Okay, pretty close. They're within a couple of centimeters. So 0.973. Okay, so that means our wavelength is somewhere between those two numbers. We'll just average them. Okay, that'll probably be the best way. So plus 0.99 divided by 2. All right, so we'll say our average wavelength is 0.982. Okay, so our wavelength is 0.982 meters. Okay, we know the frequency of the sound because it was on the tuning fork. Okay, 349.2. Can I calculate the speed of sound? All right, so I just go V equals F times lambda. I take my 349.2 and I multiply it by 0.982 meters. Okay, and that'll give me the speed of sound in here. So 349.2. All right, that's just about right on. Okay, it's about 20 degrees in here. Should be around 343 meters per second. That's pretty darn close. Okay, this is why you take physics. Physics is the science that always works. Okay, yeah. If it blows up, it's chemistry. If it's green, it's biology. If it works, it's physics. You can tell that to your other science teachers. They have a different rhyme for whatever science they're in. Okay. All right, so what we're doing here, guys, is we're just using the properties that we can find of a standing wave in an air column, right? Because a standing wave pattern in an air column is very similar to a standing wave on a spring, okay? Just like we made this morning with the spring. So, okay, that's what we're doing here, okay? What we have to remember is the first sound that we hear in a closed air column represents 1/4 of a wavelength, which is why on your formula sheet, you have this formula. Okay, for a closed air column, lambda equals 4 times the length of the tube because the tube's length is 1/4. If I multiply the tube's length by 4, I will get the full wavelength of the sound. Right? So that formula is on your formula sheet and it applies to closed air columns. Open air columns work differently, okay? Which we'll talk about here in just a sec. All right. Everybody all right with that idea? All right, here's another thing we have to remember about closed air columns. Okay, this is F1. Okay, but this is F3. This is 1/4, 3/4. This is F5. It's 5/4. This is F7. Okay, 7/4 of a wavelength. Right. This type of air column only resonates at odd frequencies because F2 is this. Okay, what do I hear at F2? Nothing. There's a standing wave there, but I don't hear it. Okay, and there were points when I was moving that column up that it made no noise at all. Okay, like it would rise to the antinode, and then as soon as I started moving away from that, it got really quiet, and it would pass a point where there was practically no sound at all, and then it would rise again to the next antinode. Right. In fact, I'll show you that with a shorter wavelength, just a little bit more obvious. All right, I'm going to go with this one. It'll hopefully produce a few more. Okay, so just listen kind of to the sound of this as it goes. You'll be able to hear the loud points and the quiet points as we go along. Oh, I missed it. Okay, you hear how it gets like really quiet, then gets really loud. Okay, all we're doing is passing the antinodes and nodes. Okay, and showing these different lengths. As I make the tube longer, I give enough room for F3 to fit in it. Okay, and then I give enough room for F4, which is quiet, to fit in it, and so on. As I lengthen the tube, I can get more and more of these patterns to show up inside. Okay, everybody all right with that idea? Okay. Okay, I think I will go over open air columns tomorrow. Okay. Okay, I don't really have time to get into open air columns today before the bell's going to go. So we'll leave it at that. Okay, remember guys, you still have your West Edmonton Mall assignment. Okay, coming up due next week, and you got your unit exam on the 14th. Okay, that's going to be on top of you before you know it, so make sure you're ready.